Today's topic of discussion is grouping of cell. Today we will note how cell is grouped in different form. So let us start. The first topic is series grouping. Series grouping in this case, first case is right grouping of cell. When each cell is in series delivers the current in the same direction, that is all cells are in discharging condition, then such type of series grouping is called right grouping of cells in series connection. Here it is shown. We have for simplicity we have taken only two cell. For here it is given this is cell 1 and this is cell 2, and both are discharging because from both current is flowing from negative terminal getting out of from the negative positive terminal, getting out of current from positive terminal in both cell. So it is in the right grouping of series grouping. Now we can write the potential difference between V and C. Vs equal to Va minus Vc equal to, now this potential difference will be equal to Va minus Vv plus Vv minus Vc. So we have written Va minus Vv plus Vc minus Vv minus Vc. Now Va minus Vv will be equal to E1 minus IR1 because current is flowing I, and plus E2 minus IR2. We have calculated earlier in the case of discharging potential difference, it's across its terminal is E minus IR, so we have used that formula. So E1 minus IR1 plus E2 minus IR2. This implies E1 plus E2 minus of I into R1 plus R2. R1 R2 are resistance, internal resistance of the cell. So this can be transformed into a equivalently a single cell whose EMF is E equivalent and internal resistance is R equivalent and current is flowing I. Then we can write VAC for this condition. VAC equal to Va minus Vc and equals to E equivalent minus I to R equivalent. Comparing 1 and 2. If we compare equation 1 and 2, then this will be equal to E equivalent. This is equal to E equivalent, and here I. So this will be equal to R equivalent. So we have, comparing 1 and 2, we have E equivalent equal to E1 plus E2, and R equivalent is equal to R1 plus R2. For example, here grouping of cell is shown in the figure. This is a 4 volt, that is EMF value is given 4 volt, and here EMF is 10 volt. Internal resistance is 1 ohm and it is 2 ohm, and it is connected with a external resistance R, and this is in the case of discharging because current direction is shown here. It is flowing like this. Also current is going in this direction, that is coming out from the positive terminal from both cells. So it will be in right grouping, right series grouping. So we use a formula to calculate the current. So here we have to find current in the circuit, second terminal voltage of the combination of the cells. So we have equation E equivalent equal to 4 plus 10 equal to 14 volt, and R equivalent to 1 ohm plus 2 ohm 13 ohm, and we know that I equal to E net by R net, that is total EMF by total resistance. So equals to E equivalent by R plus R equivalent. Total resistance is external plus internal. So 40 plus 4 plus 3 equal to 40 by 7 equal to 2 ampere. That is current in the circuit is 2 ampere. Now terminal voltage, that is PD across 4 ohm. This is the terminal voltage will be called the potential difference between this resistor. So we have to write, we know that E equivalent equals to that is terminal voltage PD across 4 ohm. This across this resistance potential difference will be equal to E equivalent minus I R equivalent. So equals to 40 minus 2 into 3, 40 minus 6 equal to 8. Well, now second method can be also be used. We know that V equal to IR. So here I is given and external resistance R is given, 2 into 4, 8 volt. From both method we can calculate. Answer. Now second, in the series grouping, wrong series grouping of cells, that is when cells are not in the same direction or in opposite direction. That is cells delivers current in opposite direction. In this case, one cell is discharging while the other is in charging condition. For example, here it is shown. This is in the. It is easy to remember that this line, that is in this one cell is discharging. You have to see the which cell is discharging and which cell is charging. So you have to for discharging you have to write E minus IR, and for discharging charging you have to write E plus IR. So here the condition is shown. This is discharging and this is the charging, and EMF is given E1 R1 internal resistance, E2 R2. Now we can write VSC, that is potential difference between A and C. VSC equal to VA minus VB plus VB minus VC. In this case, here current is flowing. It means that it is connected with some resistance, external resistance, which is not shown here. But because current is flowing, then you have to understand itself that it is connected with another resistance. That is, it shows a part of a closed circuit, electrical circuit. So VSC, that is potential difference between A and C, will be equal to VA minus VB plus VB minus VC. This is equation 1. Now we know that VA minus VB, because it is in discharging case, C1 minus IR1, and this is in the charging case. So VB minus VC will be minus E2 and minus of I into R2, because since VC minus VB equal to EC E2 plus IR2. So we have written here. Now we have, so VSC equal to E1 minus IR1 plus minus of E2 minus IR2 equals to E1 minus E2, or minus of I into R1 plus R2. Now from figure, VSC equal to VA minus VC, or E equivalent minus I into R equivalent. We have taken equivalent cell. So comparing A and B, we get E equivalent equal to E1 minus E2 and R equivalent equal to R1 plus R2. For example, find the current in the circuit. Second, PD across 4 ohm resistor. Here it is shown that it is 10 volt and it is 4 volt. Now current is flowing in this direction. So I first we have to calculate I equal to E net by R net, or E equivalent by R plus R equivalent. So we have E equivalent equal to, this is of higher potential, to 10 minus 4 divided by 4 plus 4 equal to 6 by 6, 1 ampere. Hence terminal voltage across this value, this resistance, will be I into R equal to 4 volt. Note, current or EMF comes out to be negative, then the direction of current will be in opposite to our assumed direction. If we get the current and EMF values as negative, then we have to change the our assumed direction. That is, will be opposite to the our assumed direction. Example, in this case, we have taken current in this direction. Okay, so we have to write I equal to E net by R naught. Now, this is because current, this is in discharging case, so it will be positive, and this is in charging case, so it will be negative. So we have 4 minus 10, but R net will be same, 4 plus 2, total internal resistance. So minus 6 by 6 equal to minus 1 ampere. So current will be opposite to assumed direction, that is cell 1 will be charging, that is in this case, because we have in our solution negative value of current is comes out, so have come, so our assume the current will be opposite to our assumed direction, that is the current will be in this direction like this. So this will be in discharging case, and this will be in charging case. Okay, so current will be in opposite direction, so that is cell 1 will be charging and cell 2 will be discharging. Next, suppose n cells, each of EMF E and internal resistance R are connected in series as shown in the figure. It is in right grouping series. So we can write I equal to E net by R net. And it is connected with external resistance R. So we can write I net equal to I net equals I equal to I net by R net. And which is will be equal to like equals to E1 plus E2 plus E3, that's En, and divided by R plus a small r1 plus a small r2 plus that's Rn. So we have because all have same EMF and same internal resistance, so we can directly use I equal to Ne divided by R plus N. Okay. Second, if polarity of M cell is reversed, then equivalent EMF will be N minus 2M into E, while total resistance is R plus NR. If in this series grouping, if we get M cells of opposite polarity, this is M cells are connected in opposite direction, then we can equivalent EMF find by this formula N minus 2M into E, while total resistance is R plus NR. Hence I will be equal to N minus 2M into E by R plus NR. Question: a copper wire of radius 0.1 mm and resistance 1 kilo ohm is connected across a power supply of 20 volt. How many electrons are transferred per second between the supply and wire? At one end. How many electrons are transferred per second between supply and wire at one end? And B, write down the current density in the wire. Here this is the situation is shown. A copper wire is connected with a cell whose cross-sectional radius is given 0.1 millimeter or 0.1 into 10 to the power minus 3 meter will be, and there is no So we have to find the, and R is given 1 kilo ohm, 1 into 10 to the power 3 ohm, and here EMF is given 20 volt. So we can here see that solution is equal to 20 volt, R equal to 1 kilo ohm. So I equal to E by R, 20 volt by 10 to the power 3. Here internal resistance is not given. So 20 volt by 10 to the power 3 ohm equal to 20 into 10 to the power minus 3 ampere, or 20 milliampere of current is flowing through the circuit. Now area equal to pi r square, or pi into 0.2 into 10 to the power minus 3 square, or pi into 0.1 into 10 to the power minus 6 meter square. Hence J equal to I by A. So we can calculate J equals to I by A, 20 into 10 to the power minus 3 by pi into 0.1 into 10 to the minus 6 ampere per meter square. Answer.